Hello guys, how are you today? Welcome to this webinar. I'm Giancarlo. I'm quite sure that many of you, I see many friends here, many friends and many students of mine. I think it's going to be fun. I'm going to present you some kind of ways of creating randomness or random workflow in Grasshopper. I don't know if you're familiar with my web page. I guess you are. If you don't, just visit junkrdm.com, where you will find many initiatives that I am conducting right now with this coronavirus lockdown that's affecting us worldwide. You will find some special offers for Grasshopper training. You see this 4x1 Grasshopper bundle, which contains basically 5 of my video courses about Grasshopper. Let me double check. Oh, okay, it's the chat. Oh, Tiziano, quanto tempo. Yeah, hi everybody. I'm not going to watch the chat line too much, also because I'm streaming on YouTube, as you know. So it's going to be difficult for me to follow all the messages, but sorry if I don't reply to your messages and the weaves that you are doing. But anyway, I was telling you there are some particular things on my website actually which will last more or less the same time span that this lockdown will still affect us. There are also many tutorials. In my web page, actually, I've created these tutorials page with the latest tutorials and webinars that I am transmitting. And there is also a downloads where you can have access to some high resolution and high definition 3D models. And then you can watch the latest news from my blog. Please familiarize with the website and also with the YouTube channel, where you will find several tutorials and webinars that I have recorded along the last years, during the last years. Most of them, sorry, are in Spanish. So if you're not, if you don't speak Spanish, I'm afraid you are going to just watch the picture. But anyway, there's plenty of material already, and I'm still uploading material. So please subscribe to the channel so you will be updated with my work. So today we are going to talk about randomness in Grasshopper. And for those of you who are already familiar with Grasshopper, you might know that Grasshopper randomness is not actually real randomness. So if you go, for example, in the sets toolbar, which is one of the principal toolbars in Grasshopper, you will find several things that allow to create randomness or pseudo-random things. So basically, I would say that the more important component is random. Then you will find, for example, this jitter here. Then you will find, for example, this random reduce and so on. You have several commands that allow to work with randomness in Grasshopper. But you can see that each time you use one of them, you see this input here, which is called seed. Okay, so each time you see something like seed in Grasshopper, it means that somehow the randomness that Grasshopper is creating depends on this parameter here. Now, this parameter is an integer number, and this integer number determines the way that values are generated inside this range, or the way that values are shuffled using this jitter inside this list, or the way that values are selected inside this list and they are called by the initial set. So everything is based on this value, which means that I'm going to simplify this a little because I don't want to talk about pseudo-randomness. But if you take into account the random and you take a look at the output that it produces, it's 0.77, yeah. So it is 0.77 for all of us. If you do the same, you will see that you get the same exact value. Not only because the range is set to 0 to 1 for all of us, but also and mainly because the seed is set to 2. So this is determining actually this value here. And if you change this with a whatever value, integer value you want to plug in here, you will see that this will affect the random value. And you can also notice that the standard seed is 2. And if I plug this cable, it will receive the value 53. If it receives 53, you have 0.41, okay? But if I set this to 2, set it back to 2, I still go back to 0.77. So this is actually not a real random value, okay? When I say random, I expect Grasshopper to provide some real random value, okay? But this is not happening with standard Grasshopper components. Now, that's why I do recommend that you eventually start using Heteroptera, because it is well, it is quite an interesting plugin, not only because of randomness, but also for some geometric things that I'm going to show you here as an introduction. Some tools, not all of them, of course. But for example, I would start with very simple things like many of us, for example, struggle with attractors in our daily practice, basically. And you can see, for example, that, well, the base principle of attraction is that you, let's say, associate a value to a specific geometry according to the distance, for example, from an attractor point or an attractor curve. Okay, this is for concentrated attractors. The attractor I call concentrated are basically based on a geometric attractor like points and curves. So with concentrated attractors, everything is based on distance. And this, for example, is something, it's a component which is called attractor that converts actually or associate a normalized value, which means basically a value between 0 and 1, to a population of points, or yes, basically a population of points, a point cloud, according to the distance from several attractors. So I'm using here, for example, this curve as an attractor, and I'm using here this point here as an attractor. And these two geometries here are determining one single value between 0 and 1 for each of the point cloud, which are all of these. Okay. So for example, if I take this point here and move it around, you will see that simply the point that surrounds this will receive a higher value because according to their distance. Okay, so it's very easy to create an attraction rule, because once you have the normalized value, you can do whatever you want. In this case, I'm creating simply a radius, but you can eventually remap these values and give them the proper range in order to use them for whatever you want to use them for. Okay, so you see, for example, this component is solving one of the basic structures in Grasshopper, which is calculating the distance and then remapping the distance and so on. So it does everything with one single step. Another thing that I wanted to show you, is always based on attraction, is this. So for example, this is a standard plane surface that you can see, for example, like here. Let me turn off the final result. So this is the initial surface. I divide the surface into 80 by 80 spans, which means 81 by 81 points, by the way. And I decide to basically create this variation here based on an attractor, which is this curve here. Okay, so basically what I do here is create a curve, divide it into points, and all these points are used as gelum. So gelum are the attractors, and particle as tree. You see that it not necessarily we need to work with a point list. In this case, it can be a tree, which is important, as you will see in a while. So if I do this, we will have all these points acting as attractors over this point cloud here. And the result is that these points are displaced in space because you see this as also the option for planar and three-dimensional. I'm using three-dimensional because the curve lies at the bottom. So I want this point to push away the points of the point cloud. And what I'm doing here is pushing this point away according to their distance from the attractor points. And so in the end, as I'm working with a data tree of points here, I will get as a result a data tree of displaced point that I can still connect, for example, with this set of curves, of NURBS curve, which represents the deformation of my original plane. And eventually, I can also rebuild a surface with a loft, for example, like this. And this is actually, for example, a very, let's say, tricky result, because as everything depends on the amount of the attractor and the distance between the attractor and the point cloud, and also the strength that I give to this gellum attractor. So if I increase this, you will see that this surface starts to inflate way too much. Okay. Also, the attractor, you see that strength, it doesn't say give me a positive value for the strength. It means that this attractor here can also work like in the opposite way, like pulling the surface. Now, in this case, for example, I wouldn't exaggerate, because else I'm going to create some self-intersection for this surface. But you see that I'm creating a negative crease for this surface downward towards the attractor points. Okay, so it's very interesting to work with this gellum attractor. It's somehow tricky. For example, I am going to change from this attractor curve to these 3 attractor points. So plug them into gellum. And we will see, for example, that now, yeah, I can increase a little more. I am creating basically some pinches on this surface. And this depends also from the distance between the points and the surface, and all the parameters that we were mentioning a few seconds ago. And the thing is that we always get this kind of result. Of course, if I switch to a positive value, this surface will start to inflate, or this point cloud will start to inflate locally, and it will give us this kind of nice deformation for this curve and for the relative surface as a result. So you see that many attraction things can also be handled by Heteroptera in a very smooth and simple way, without, let's say, long constructions and long sets of components in Grasshopper. Of course, this is also, only valid for some specific scenarios. Okay, you cannot solve any attractor rules by creating these kind of simple structures in Heteroptera. But Heteroptera not only works with geometry. You see that I was discussing some components from the geometrical group of tools. It can also deal with mathematics, and this is very interesting, because there are several components here that I normally use in my workflow that allow to create some nice effects. For example, this one, which is basically, I'm sure you are used to work with the Graph Mapper. Actually, there are already some plugins, like, for example, the Graph Mapper. There is also another plugin which is called Rich Graph Mapper. You can see here the function as it looks like when you place it into the canvas. But in this case, for example, what I'm doing, I'm using an Hetero Mapper, which is basically this one. This is very nice because it allows to define the graph curve like any other curve in Grasshopper. So for example, in this case, I'm using this curve, which is the representation, the normalized representation of this one. But this aspect here depends on the distribution of these points. Okay, so I have a set of variable points which determine the shape of this curve, which is being used for the remapping of input domain and output domain numbers. Okay, so this is something very cool, and I do recommend that you play around with this. So, for example, you see I am, let's say, binding the aspect of this curve and the output numbers that I get from the Hetero Mapper to the radius of these circles here. So, for example, if I take a look at this curve, I expect the radius to increase and decrease with this very particular shape. So the speed by which it increases it's faster than the speed of decreasing the values. Okay, so if I take this, for example, and take this middle point here and move it down, you see that I am changing the shape of the graph, which is reflected here. And this means that the numbers are being remapped in the output domain, falling down in this central area, which affects the center part of this circle. Now, how does this thing work? It creates a graph with a rectangle here. You see that normally I tend to work with normalized values because I think it's the best workflow in Grasshopper. I don't want the elaboration and the script to depend on specific numeric ranges. I prefer eventually to remap values after these operations here. And you see that, for example, the boundary rectangle is created dynamically around the graph of this curve. So if I, for example, decrease this height way too much, you see that the rectangle is adapting, because this will always work with a normalized domain. It takes this boundary rectangle and converts it into a square measuring 1 by 1. Okay, so this is very common when you work with normalized numeric domains. So you should understand what this means. And you see that everything is basically scaling down to the numeric range 0, 1. Sorry. So you can see that you can change basically whatever kind of variation. Of course, the only thing that you cannot do, but this is also a consideration that affects the standard graph mapper, you cannot, for example, create a curve that simply goes backwards along the x-axis. So if I take this point, for example, and move it to the right, and take this and move it to the left, then this will create some kind of weird behavior in the hetero mapper. So don't do this. Okay, so it's just making things work badly. Okay, and another component that I wanted to show you here is a further elaboration, which is called the number bias, which is basically a way of redistributing these values towards the beginning or the end of the value sets. So, for example, what happens here? Well, I'm leaving the graph on. So what this value does is redistribute this number that come out from the hetero mapper according to this graph here, which is basically creating a new balance between inside this list of values. So if I take this, for example, you see that this graph is changing in the opposite way. So basically, concentrating this bias towards the first number of the list, it means that we are preferring the highest values, okay? Sorry, the lowest values, okay? So you see that all the circles get smaller inside along the first part and the last part. So it's like basically scaling this curve down towards the x-axis. While on the other hand, if I increase the bias number, what I'm doing basically is flattening this curve over the top side of this boundary rectangle. Okay, so you see that all the circle starts to inflate accordingly. There is always a increasing decreasing factor here, but you see that it inflates towards the upper values. So this is something very nice. And you can also work with a bipolar, which is basically a symmetric graph. We can simplify things like this. So you see that this graph is basically a anti-symmetric, but you can switch to bipolar and you have a symmetrical bell in this case. And you see that it's the same effect, but it's symmetrical to according to the mid values, okay? So it depends on the distribution of values. You can decide which of the two things you prefer. In this case, I simply switch back to the cubic factor because it looks nice. One simple consideration, one stupid consideration. This is somehow this has a bug. Which, by the way, if you don't turn the preview off and you disable all this part of the definition, the preview of this component will stay on. So I prefer to turn the preview off and then turn off disable all these components here. And one last thing that I wanted to show you about this math is this component, which is something we normally struggle a lot. It's called list normalizer. If you want, for example, to remap a list of values, and you want to remap them inside a target domain, which is by default 0 to 1, instead of working with the remap numbers, you can simply plug your list of values inside the list normalizer, and you get automatically these values remapped inside the 0 to 1 domain. Okay, so this simplifies this remapping to a target domain of 0 to 1 with one single step. Okay, so I can simply show you this. I will create a stupid series of values like this, plug them here, and as a result, we get values between 0 and 1, and as many values as we have inside our list. So 10 values, you see 10 values between 0 and 1. Okay, so yeah, basically this is something that simplifies some simple processes. And before switching to this definition here, which is the one that you saw, for example, in the preview of our of our course, which is this one. I'm going to talk about this one later on. I wanted to show you another thing that is very important and something that I normally use in my workflow as well, which is basically something about networks and, of course, something about uncertainty. We will not talk about, let's say, the generative processes like the utilities here. This is something that it would take quite a bunch of time to implement definitions that work with this thing, but it's very nice to work with this component. There are also funny components like, for example, ovulate. But anyway, networks, I would concentrate only on two of all these. There are some very complex comments here, like those about topology, connection, but I would eventually illustrate only the incestuous network and the non-incestuous network, because they are some nice comments. Normally, for example, if you have a set of points like this one, and you want to create interconnections between them, eventually you might know that there are some commands in the mesh toolbar in the triangulation, which are called Delaunay. And Delaunay basically creates triangular connection between all these points inside this network. Okay. Now, this is something that can be useful, of course, but in my case, I want to point out a different method for creating interconnections, which are more interesting, because this is automatic. There is no way of controlling this interconnection scheme. Okay. So, for example, if I take this incestuous network, and I will point out the difference between incestuous and non-incestuous in a while. But if I take this population of points and plug them into points, you see that I'm creating this, let's say, weird interconnection scheme. For those of you who are, let's say, used to work with the data manipulation, you might recognize, for example, that this is something that you create with this cross-reference component here. So you are basically connecting each of the point belonging to this population with all the remaining points. Okay, so if you have 100 points in this population, you are creating 99 connections for each point, which is creating this orgy of lines. Okay, but we don't want this. Okay, so the method that you use inside Incestuous Network is to create connection by distance and specifying the number of connections that you want to generate around each of the point cloud. So, for example, if I want to create a connections only up to a specific distance, like, for example, well, this region measures 20 by 10. So I'm going to take a slider 2.00 in order to have a range between 0 and 10. And I plug this to distance. Now, you see that Incestuous Networks is creating connections only between those points that are at a maximum distance of 2. Okay, so if I increase this, I allow more and more connections. Okay, but if I decrease this, I am controlling which points are connected. Well, not which points exactly, because this is a random or pseudo-random population. You see there is this seed actually, and I am controlling at what distance I want to create the connections. Okay, so in this case, I can create some interesting connection scheme. Now, the only problem with this type of components here is that, for example, in this case, I'm creating a clean scheme, which means basically that I have a clean connection diagram, you see. But if I increase this a little more, some weird things start to happen. For example, these. Okay, so these are basically two intersecting connections that eventually I don't want to have in this scheme. This is something that you cannot control actually using simply the distance. Okay, so in that case, for example, if you don't want this, you see that you can work with the number of connections. For example, this point actually is creating 1, 2, 3, 4, and 5 connections. But if I use a slider like set to 4 and plug it into number, I make this diagonal connection disappear. Okay, so in this case, for example, I can control how many connections I want to create around each of the points. Of course, this is a maximum amount of connection. There are some points that just connect to 1 because of the distance, but those that are, let's say, surrounded by let's say, several points can create a maximum of 4 connection lines. Okay, so if I increase this, you see that the 5th connection can appear, and you can say, like here, in a regular distribution of connection, radial like this, but you can also encounter this kind of weird situations that I prefer to avoid. Okay. And then there is the non-incestuous network. Now, incestuous network means that the connection or the network is created inside the same set of points. Okay, so that's why it's called incestuous. The alternative is to work with non-incestuous network. And let me turn off this, and let's work a while with non-incestuous network. What I'm going to do right now, I want to create connections between points belonging to different sets. And in order to do this, I'm going to create a series of curves, like, for example, these, and I'm creating this. I'm doing something weird on purpose. So like this, with a variable distance, of course, because I want to point out all the parameters of this thing. Well, enough with this. So I'm importing multiple curves, and I'm internalizing these so I can share the definition with you at the end of this tutorial. So what I have here is a set of curve. You know that if I divide these, I get a set of points, of division point per curve. So I am getting 6 branches here, each one containing 11 division points. So I can decide how many points I want per curve. So I can decide, for example, how many points will belong. 28 points means 28 spans means 29 points. Okay, so I want to work with these sets of points, and I'm not going to flatten this value here because points ask for points as a tree, and of course because it has to establish the relationship between several sets of points. By the way, this is exactly the icon referring to this situation here. So if I plug this, and fortunately, this component doesn't work automatically until I define a distance. Number is set to 1 by default, but distance, you must provide it. And this is good because in this case, the amount of relation would be enormous, okay? So for example, as per the distance, you see that here we have a distance of 15 more or less. So I'm going to take something like a 11 slider and set it to 0 initially. So this thing is starting to work. And as I increase this value, the first connections start to appear for those points that belongs to separate sets and have a distance between a maximum distance of 1.51. Okay, so if I increase this, you see that I start creating this thing. And if I increase too much, I start to create this kind of weird connection that are jumping from one curve to the third one, for example. Okay, so I don't want to do this, and that's why we have control over the distance. You can also play around with this. Oh, and of course you have the number of connections. Now this is set to 1 by default, but you can set to any value. I prefer to don't increase this too much, or else you will get some weird result. But you can see that this thing allows to create some nice graphic solution for your geometry here for your system. Okay, so it's quite chaotic if you exaggerate with these values, but at the same time it allows to have more control than automatic connection schemes, like for example Delaunay. Okay, so in this case, for example, I would recommend that you start playing with this and see how you can push the limit and get to the desired result that you want to achieve with your definitions. And the other thing that I wanted to point out is basically true, or well, let's make it clear, there is no absolute randomness, okay? So the Heteroptera is a step forward towards randomness, but it's not absolutely random, okay? So when you go inside the uncertainty group of components, you will find all that's random in Heteroptera, okay? There are always components that allow to work with attraction rules, like for example, attractor geometrical possibility, bias distributor. I invite you to familiarize with these components, which are quite interesting. But what I want to do is basically work with, give you an alternative to Grasshopper randomness using this plugin here. So for example, here we have randomized number. We also have a different random generator, which is different from Grasshopper standard random, but you see that they are quite similar also in the icon. Okay. Another thing that I wanted to show you is the seed generator. So these three components are basically quite relevant in terms of values, the random values generators. These, for example, randomized number, it takes a set of numbers, and basically it shuffles those numbers, or basically give them a variation. Well, no, it's not shuffling, it's giving them a variation. Okay, so for example, if I take a control value like a number slider, like this, and I take a look at the output, you see that starting from 2, I get 1.81. Okay, this is due to the ratio. The ratio is like a percentage. Okay, so if I take a small value for this ratio, I get a result which is more similar to the initial value. So this is a normalized value. As you can see, it says range 0 to 1. So I provide a slider between 0 to 1, which by the way is called normalized slider. If I say 0, there is no randomizing, okay, no blurring of this value. But if I start to increase it, you see I get random values dancing around the initial values. And you can see that in this case, for example, if I switch from, from 0 to, 0 is 2, okay? But if I switch to 0.1, I get 2.02, or 2.026, okay? If I switch back to 0, of course, I go back to 2. If I switch back to 0.1, I get 2.16, not 2.02. So this is something that is very interesting, because the seed, which is optional, by the way, it's empty. So these random components from Heteroptera work differently from Grasshopper standard random component, which are totally based on the seed. And for example, you will notice also that if I take these and copy paste it, the simple copy paste with the same inputs is outputting a different value. With the same inputs, I get a different value. Now, this is something very interesting, because these allow to create a better random workflow in Grasshopper, even without using the seed, which by the way is almost always optional in Heteroptera. So you see that this is quite crazy, because I have struggled for years to create, let's say, a more random behavior in Grasshopper before knowing Heteroptera. Okay, so I will leave this like here, and I will also show you that when you hit F5, or basically when you recompute your solution, Heteroptera component update and give you a different result from their elaboration. Okay, so you see that it's very nice to work with this, because it simplifies somehow things. But you can also see that when you hit F5, values get aligned in this case. So I have the same component, I am refreshing the definition, and I start to have the same value as the output. Why? I think, I am not sure, I've not spoken with the developer of Heteroptera, but I suppose that the randomizing that happens here in these components and also in the other one depends also on the time in which you place the component inside your canvas. Okay, so that creates basically some internal seed that changes when you copy paste, for example, your component. But when you recompute your solution, for example, your definition, you are basically refreshing time, and the time is basically set as equal for all the components. And that's why I suppose that this is actually outputting the same values. But it's very easy to go back to the same situation, because if I, for example, unplug the ratio to this, I get these different values here, and I go back to randomness. Okay, you see. So there is no, basically, if you want to work with equal values, you have to do it on purpose in Heteroptera. It's very unlikely that you get equal random values from Heteroptera component. The other one that I want to show you is the random values generator. Okay, you see that this is set actually to absolute value. You can also create bipolar value. So absolute value means that you get positive values between 0 and 1. And bipolar values means that you have values between -1 and 1. And the only thing that you must define is how many numbers you want to get from the random generator. So actually it's set to 10. If I take a panel here and plug this, I get random values between 0 and 1 because it's absolute value. If I switch to bipolar, I have random values between -1 and +1. Okay, and if I hit F5, I'm getting several different sets of values from this random generator. And you can simply plug a slider here to define how many values you want from this component here. Each time I change this value, for example, 27, first value is 0.996. If I switch to 28, first value is no longer 0.996. So you see that every change you make here gives you a different set of random values. Okay, so I prefer by far to work with this random generator rather than using standard Grasshopper components. And then there is this one. Now this is very nice to work with because it allows to create a random integer values that you can use as seeds. Now, why would you use this? Well, eventually, for those of you who will assist to the next webinar, which is about loops, we will be working with this seed generator in order to create several variations inside our loops. So what does this function is basically each time I refresh the definition with F5, I get a different value, a different random value with very high values, which is a good thing for the seeds. Because seeds tend to create some repetition. So I don't know if you're familiar with this, but if I take a simple random value generator from Grasshopper, if I work with low values, I tend to have some repetition inside Grasshopper. So for example, in order to make it clear, if I take a populate 2D and I decide, for example, to work with a few points, like for example 1. Well, let's take a slider and bring it down to 1, and you have the seed. Okay, so if I take a seed value between 0 and let's say 1000, okay, and plug it into seed, I have a different position for the random point inside my region. But if I start to move this, you would see that this point is basically moving in diagonals, as you would see. Okay, so this seed is actually it's a progressive value, of course, but when you work with a small range, where small for a seed means, for example, 1000 is a small range for a seed, you can start to observe this kind of weird phenomenon when you have randomness, but it is some kind of weird randomness. Okay, so this is not happening if you work with a random seed generator, for example, like this one. Each time you refresh this, you will have your point appearing in different positions, as you can see. I am refreshing it in real time with the F5 button. So you will see that points don't appear in a recognizable pattern. Okay, so I do prefer to work with this seed generator in order to create true randomness, also in standard Grasshopper components. Okay, there is no component here in Heteroptera that can create this kind of point cloud randomly inside a region. So you have to work with this. The point is that you can parameterize the seed with some Heteroptera component like the seed generator. Okay, so yeah, as you can see, this simple 3-component here basically allow to create a better random workflow inside Grasshopper. Basically, there is another thing that's very important in Heteroptera as regard uncertainty, which is random directions. Okay, so for example, you see here we have random direction and random vector. They are quite similar. I will grab the two of them so that you will have a look at what's the difference between them. They both create 3-dimensional vectors, okay? But one only asks for how many vectors you want, and the other one, the length of your vector. So for example, you can use them for, I don't know, whatever kind of application it comes to your mind, but let's take a look at these vectors. So in order to understand how they behave. So let's take a point here and let's set it to 0. And let's anchor this and let's take a look at these vectors here. Now, This is basically a set of three-dimensional vectors. We can take a look at them in perspective. So you will see that it's basically a spherical distribution of vectors. Okay, you can decide how many vectors you want. So let's take a look at these. You see that each time I change this slider, all the vector, not only are some vectors are added or deleted, but all the vectors shuffle once again. Okay, so each time you refresh or you change some values inside Heteroptera component, everything gets shuffled and you get a totally different distribution of values or random vectors in this case. So this creates only three-dimensional vectors. You can also switch to planar if you want. So actually, I'm creating a star of vector pointing in a random direction around the point 0, and with the same length, which is a normalized length measuring 1, as you can see. Okay, so these are basically vectors that you can use for some kind of strange things. I don't know, just to work with a very simple workflow. If I take this circle and divide this circle by the same amount of vectors that I am creating, I can create a set of points that corresponds to the same set of vectors. Well, not eventually. Someone is drawing. Please don't do that. So actually, what I'm doing here is creating a regular set of division point because of the divide curve, but I have an irregular set of vectors which are randomly distributed in the 360-degree area. Okay, but I don't care about this. I don't want to work with this geometry right now. It's just to give you a glimpse of what you eventually could achieve. So if, for example, I move each of these points with one of these vectors here, I start to create this kind of random distribution inside my points. And eventually, I can also play around. Randomness is fun because you can work with it to create some weird result. So I am switching between a regular circle to this totally chaotic NURBS curve. Okay, and this is something that I am doing in 2D, but I can also switch to three-dimensional in order to have some kind of weird structures. This is something that, for those of you who are into arts or digital media, this might begin to sound interesting. Okay, because this kind of random variation is something that you can work with, and eventually you can hit F5. Each time you hit F5, you have a new distribution of values, of vectors, sorry, and therefore a different distribution of points and a different shape for your final NURBS curve. And on the other hand, there is this other component here, which is random vector. Let's take a look at what it does. It's basically the same thing, but you have another parameter, which is length. Okay, and length is not a value, is a range. So you can define the range of variation for the length of each of these vectors. So, for example, length in this case is set to the domain 1 to 5. So the smallest vector can be 1, and the largest vector can be 5. Of course, you don't have this kind of values. Eventually, if you measure the length of these vectors, vector length, you will see that you have random values between 1 and 5, as you can see, not necessarily 1 and 5. Okay, so for example, you can change this. You know that if you define a domain only by a single value, you will get a domain between 0 and that value. So if I take a slider like 11, the domain gets to 0 to 11, and I can change, for example, the variation for this vector. As always, you can see that in the moment I change something, everything shuffles. And the number of vectors, this is quite pretty straightforward. You decide how many vectors you want to create inside this range. Okay, so this is something that's also very nice. There is also another component, which is wandering vector. So for those of you who want to play around with animations or animated drawings in Grasshopper, you can work with this wandering vector. Sorry, I missed the alt. Yeah, like this. So for example, wandering vector is like this. Let's take a look at it. So it's a set of vectors which is changing over time with a specific time span. Well, in this case, it's set to normal, which is 32 milliseconds, but you can make it fast, 8 milliseconds, like this. And you can decide also how fast is the variation between one iteration and the next iteration. So each vector is basically moving around randomly, okay, but with some kind of smoothness, okay, and this smoothness is set by likelihood, okay. So for example, if I set this to I don't know, likelihood is actually set to 0.3. If I set it to a slider 0 to 1, so likelihood 0 means that you see the vector, the movement of the vector is very, very smooth, okay? But if I set this to 1, is that these vectors start to bounce around very quickly from one position to another, okay? And then there is steps. Steps means how many, this affects the smoothness as well. It says basically how many iterations are needed for a vector to change completely its direction, okay? So steps is set to 40, for example. If I set it to a slider between 1 and 100, you see that actually in one single step, let's take a look. You see that steps 1 actually avoid these vectors to move around, but if I take step 2, you see that the variation is very, very quick, because in 2 steps, from one step to the other one, there is a total shuffling of the actual version of the vectors. The higher this value, the smoother the animation becomes. And this is because basically it takes 100 iterations to change the distribution of vector completely, okay? So this means that in 100 steps, you have the vector is basically respecting its previous positions, okay? And so this makes it smoother for our vectors, okay? So with this, you can play around and do some nice things. Eventually, not exactly in this moment, but if we take, for example, our point, okay, our center point, and move it using these vectors here, we have one point that's being moved a number of times which corresponds to 10. So I have 10 wandering points in this moment. I don't want to see the vector, I just want to see the points, okay? So you have this set of 10 wandering points. And if I start, for example, recording with a data recorder, if I start recording this geometry, I start to get these things here. So this is a very basic principle that allows me to introduce, for example, the some very simple growth algorithm, okay? In this moment, for example, we get, as you can see, a very simple set of points, which is basically a list. You can recognize it by this type of wire representation. So it's a one single set of points, okay? But if I stop recording, clean the data, and then take these 10 points and split them into a data tree, each branch contains 1 point. When I start to record this, I get 1 branch per each point. And if I do this, and for example, stop recording, hide this, and use, for example, a polyline to connect these points, you see that I start to get some random growing polylines. Okay, we can take a look at this in a better way by making visible only the polyline components. Okay, so for example, if I do this, you see that I have random polylines coming out from my set of points. How many polylines? Well, it depends on the amount of points that I want to create in the random vector, sorry. So if I take a small value for this slider, like 2, I can still record this, and I have 2 changing polylines in this growing shape, okay, distribution. So this is a very basic growth algorithm. For those of you who already know my growth video course, this is basically that's how it starts basically. But of course, there are many complex ways of creating growth behaviors in Grasshopper. For those of you who want, you can take a look at my webpage here, and you will find it's basically this course here, which is actually basically on for sale because of this coronavirus lockdown. But I do recommend that if you want to buy one of these video courses here, you take a look at this 5x1 Grasshopper bundle because it contains, for example, the growth. So for example, in this case, for the same price, you get 5 video courses instead of this one. But anyway, little commercial spot. So anyway, this is eventually a nice algorithm that you can implement without using iterations, as you can see, because the iterations are contained inside the wandering vector. Okay, and the last thing that I wanted to show you is actually the definition that's creating the image from the webinar. Now, this is actually 2 different scripts in one. And it's using a Heteroptera component, which is this one, which is called noise oscillator. Okay, so if you take a look here, you will find the noise oscillator here, close to the wandering vector. Okay, so these are very nice components. These that we are discussing right now. So I'm going to show you what this component does. It's like having a wandering vector, but it creates just changing values inside some specific domain. Okay, so by default, you see we have this control over the speed by which this component refreshes, which is basically the same that we had in this in our wandering vector, and it emits basically normalized values. Okay, so between you see that is negative and positive values, but they are between -1 and +1. Okay, so this is what the noise oscillator does. And what I'm doing here, I'm using this component here for 2 different things. First one, I am creating some bubbles inside this rectangle here. So you see basically that the noise oscillator is giving me basically 1 value per each point that I get from this square grid. So first I create a square grid with this control for the size of the squares, and for the extent I get 20 by 20 squares. Okay, and you know that when you have a square grid, points are not at the center of the squares of the cells, they lie at the corners of the cells. So if we take a look at this, we have corner points and not center point for this, which means, by the way, that if we take 20 by 20 spans or 20 by 20 cells, we will get, here you can see 441, which is 21 by 21 corner points. Okay, this is important to notice, to observe, because when we create a noise oscillator, in order to associate 1 value to each of the points of this grid, we will have to take 20 and basically use an expression which is 20 plus 1 square, because we need the same amount of random values as the amount of points that we get from this grid. Okay, once we have these, I am multiplying this random value by a multiplication factor, and I'm using this value as the radius of a circle whose center is given by the corner points of our square grid. So I get this. And this is basically a set of circles that changes its size in time because of the noise oscillator. This multiplier here allows to create some scaling up or down of these circles. So I set this to a range between 0 and 1. So with 0, everything disappears. With very small values, I start to have very, very small changing circles here. If I start to increase this, I am basically scaling the globally all the circles down with this scale factor. But I can also scale them up, like double its original size, like this. And of course, I start to create this kind of a nice behavior, like if it was raindrops or something that happens in a specific time and then tends to disappear because of this random oscillation. Of course, this is not exactly true, because if you have a droplet, for example, falling on a surface of water, the circle should enlarge and then shrink down once again. But the size of these circles here is changing randomly, okay? So it can increase the size, decrease the size randomly. But anyway, this is just to like random comments. Okay, so in this case, what I'm doing here, I'm calculating the convex hull, which is basically the outline of this square grid. So I just want the outline, the outer border, and I do it with a convex hull, which is creating this rectangular curve. And I'm using this to trim the outer circles. I don't want the circles to, let's say, pass through the outline of this rectangle. So I trim with region, and what I get are these curves, which are perfectly contained inside my rectangular area. Okay, so this is one use of our noise oscillator. The other one, it's basically, I would say, almost the same, but it's a, well, speaking of talking about complexity now, it's ridiculous. But anyway, what I did here was take the cells, the square cells of my grid, calculate the vertices using the discontinuity component and not the explode component, because when you have a closed curve, if you explode that curve, you will have a set of 5 vertices per curve because it's closed one. So the first control point or the first vertex corresponds to it's coincident with the last vertex. So you get double. One vertex is being counted 2 times. Okay, and in this case, discontinuity only detects the actual vertices, which are 4. And then I take this list item with index number 0 in order to isolate only the first of the vertices, okay? Which is, by the way, the lower left vertex of this square cell for each cell. And then I use this to create these arcs. Now, the radius of the arc is set by the same size of the square cell. Okay, so I am sure, for example, that I have basically this arc is being created like half the size of the square cell as radius. Okay, and then I start to perform well, and the arc has an angle of 90 degrees. Okay, so it goes from the lower side to the left side, and therefore what I do with this is basically rotate it. And if I rotate this arc, I am creating here a rotation around the center of my square. So in order to have it visible, let's visualize the square as well. So I draw this arc and rotate it with an angle of 2 times p, which is basically having here some kind of mirror. Okay, if you think about it. Okay, and I want basically to create two repetition. Sorry, an array, not a rotation. Okay, so I'm creating an array with 2 copies of the original item in 360 degrees. So therefore, I get these 2 mirrored arcs. And once I have this, I need to take this and rotate them, but I am rotating them randomly with a changing value. Now, in order to have this kind of variation here, if I have a, well, let's draw it here in Grasshopper, it's quicker. If I have this thing here, and I have created basically this arc and this arc, I have just 2 possibilities here for this geometry. It can be either oriented like this, or it can be oriented on the other hand, like this. So according to this random rotation that I am producing, the next square here could have the same rotation as this one, and therefore create this thing here, or it can have a different rotation like this one, and therefore it will create something like this. So if I distribute this randomly inside the whole grid, I have this kind of dancing pattern here made up of these nice, let's say, polycurves that can be used for whatever kind of application you want. In this case, for example, I am taking the noise oscillator, and I am using basically the values that I get from here are being converted into the absolute and round value. Basically, I am eliminating somehow all the decimal values that I get after the first decimal number, after the comma. Okay, and then I'm using this simple Python script because this is doing nothing but it says if x, meaning the value that is getting in, is equal to 0, then a, which is the output, is set to 0. If x is equal to 1, a will be 180, and if it is something in between, it will be 90. Okay, so this is what happens here. This is outputting values of 0, 90, or 180 according to the values that we get from this shuffled set of values. So basically, I am creating here a set of 400 angles, because remember that our array happens inside one square, one cell. So each pair of curves corresponds to one square. So we have here, for example, two curves per each square, which is a data tree with 400 branches, okay? And therefore, we need 400 values for the rotation of this, for the rotational angle. And also we need these 400 center points, which is one per each square cell. So you can see that this is the output for this function here, for this script, which is basically creating this moving pattern of these polycurves. Of course, these are not exactly polycurves in this moment because they are simply disconnected arc. They can be joined together if you want with a joint curve. But remember that if you do this, you have to flatten this and have access to this smaller set of curves. So in this case, for example, we can isolate one of them like this and see that we have this random curve moving around this this square. But anyway, this is just for let's say completing this dissertation. But anyway, the important thing here, I suppose, is this one. Okay. So as you can see, you can do plenty of things. Now, I just want to let's say give you a quick perspective of this plugin. Actually, this is something that you can also use. Heteroptera, it's something that you can use, and you should use it also for some generative design application. And when you browse this part of the plugin, you will see that you have some nice components, some nice functions. That, for example, you see that ovulate is basically a function that allows you to create a different distribution of parameters, a different set of parameters that are affecting your design. So each time, for example, you will take ovulate and say, please ovulate, it will take all the values and all the parameters that you are using in your definition, change them randomly, so shuffles those values and give you a different design, different result for your design. And also you have the quick baker, which is basically something that you can use to create a baking of all the variations of your design dynamically without having to change the values by hand. So for example, in this case, in this definition, if I change, for example, the extension, well, the size of my grid, or I change the extension of the grid, you see that I am changing the result. But if I want to bake, for example, this result, I should go to the bottom of the definition, right-click, and bake. Now, these two components allow to create several bakings of the same design by changing the values that are defining each variation of the design. So you don't need to go back and forth in your definition to create this kind of variations. That's why it's interesting to work with this in order to have some kind of generative design approach. Okay, so see what's the variation of your design according to initial parameter. This makes it easier to get this kind of perspective in your workflow. And there are also other components that are generally utilities that allows to work with sets and numbers and also with some text. As you can see, you can bake a string with this one. But anyway, this is just for some future development of the use of Heteroptera in your workflow. I do recommend that you start using and play around with Heteroptera. As always, I will be sharing this definition in my website. And also in the description of this video that, by the way, is being recorded and it will be available on my YouTube channel. So yeah, that's pretty it. I don't know if let's switch quickly to to the chat. Oh, there are 6 messages. Let me check here. Okay. Yeah, Leonardo, for sure. Tiziano, how do you draw the initial curve inside that mapper component? It's whatever curve you might want to use, Tiziano. So if I go back to this, for example, like here, the curve is defined by this. So this curve is basically a parametric curve that I can change as much as I want, as you can see. It's defined by this set of points. So I can change this set of points. This will affect this curve that is being used by the Hetero Mapper, which is, I think, the more complete graph mapper that you can have. Of course, you can work with random organic curves like this one, or you can work with controlled curve, like, for example, a straight line if you want. So if I take, for example, a couple of points, like set multiple points, like this, and then polyline them like this, I get one single segment, and I can work with it like this. You see? So I'm using a extremely regular curve, which is basically like using a graph mapper with a linear graph. Okay, so you can create a curve with whatever technique you might want to use, and it gives you access to a whole range of possibilities, as you can see. Okay, you're welcome. Wandering vector and yeah, oh my God, wandering vector and all the possibilities. Yes, exactly. Yeah, overlap component. It's yeah, I agree. Can the oscillator somehow be stopped from updating continuously? Well, actually, this is something that we will discuss in the loops webinar, because all of these components here are constantly refreshing. So if you go here and you take a look at this, you will see that there is a self engine off, okay? That you can stop it from creating random values, as well as you can stop, for example, also the wandering vector, self engine off. The problem is that you have to do it manually. And as these updates, like between 8 milliseconds and 96 milliseconds, which, by the way, is, even if it's slow, is extremely fast, okay? There is no way that you can turn the self engine off on time in order to stop this your definition from running in the exact moment when you need to stop it. Okay, so it's very difficult to handle this, like turning off the self engine. There are other tricks that you might want to adopt, and especially we will discuss this when we will be dealing with the loops in the next webinar. Okay, so you explore generative design in your growth course. Well, actually, more than generative design, it's more growth algorithms. So, for example, let me think about it. If I can show you some growth examples quickly. So let's go to here. Let's go to here. Let's go to here. And let's say this growth should be from well, 2019. And Grasshopper growth. Oh, these are just some screenshots from the it's the cover basically of the recorded classes that you will access if you subscribe. So this is the session 1 where you have this kind of growth algorithms, which are some kind of basic algorithm. Then you have this one, which is like working with several techniques for creating growth behavior. And then there is this one, which is the last one, the more complex one, which is based on Python, basically, and different mesh representation in order to create this kind of 3-dimensional growth inside or in a controlled environment, okay? So this is basically what's discussed inside the growth video course. But the possibilities are basically, well, I wouldn't say infinite, but yes, more or less. No, I didn't share the Grasshopper file already. It will be available on YouTube and on my website. I will share the link on my social networks later on today, as soon as I encode the video and publish it on my YouTube channel. The growth is genetic growth algorithm. Well, I don't know what you mean about genetic, but yes, there are several parameters that can affect the result of your of the growth geometry. Okay, so yeah, it's differential growth. For example, the last picture that I was showing you, especially the mesh result, the three-dimensional mesh, it's differential growth in a controlled environment. Yes, absolutely. So everything is explained over there. The type of mesh representation that you need in order to implement that kind of growth, and also the Python code needed to develop that kind of differential growth. You're welcome. Okay, so I see. Let me double check if there is something here on YouTube as well. Let me double check. Oh, okay. Yeah, there was some weaving here. Okay, but no question. So that's good. So yeah, basically that's it. That's it for the webinar, guys. So thank you for being here, and thank you for your interest in my things. I do recommend that you subscribe to the channel, and let's stay in touch. Thank you, Leonardo. Whatever question or doubt, just drop me a line, and I will be more than happy to discuss things with you. And eventually, if there is some nice and relevant question, maybe we can organize one other webinar. Who knows? Thank you very much, guys. Have a nice day, evening, wherever you are. Bye.